In this lecture, we are going to discuss an important nonlinear first-order ordinary differential equation, which is called Bernoulli equation. It has the following standard form: y prime plus p of x times y equals f of x times y to the n, where n is not equal to 0 or 1. So y to the n is the nonlinear term. For example, y prime plus y over x equals x times y squared is a Bernoulli differential equation. Here, p of x equals 1 over x, f of x equals x, and n equals 2. The equation is named after Jacob Bernoulli, who lived in 1655 to 1705, a famous Swiss mathematician from the famous Bernoulli family, who discussed it in 1695. Bernoulli equations are special because they are nonlinear differential equations with known exact solutions. A famous special case of Bernoulli equation is the logistic differential equation, which is used in the restricted growth of population model. And this would be the topic of our study in lecture 7. Note: y of x equals 0 is a constant solution of a Bernoulli equation 6.1.1. For n equals 0, the equation 6.1.1 reduces to a first-order linear ordinary differential equation of this form. For n equal 1, the equation 6.1.1 reduces to the following form: which can be written in the following separable form. Method of solution: if n not equals to 1 in equation 6.1.1, then it can be rewritten in this form, just by dividing the equation through the quantity y to the n. As shown in equation 6.1.2. Now we define a new variable u by y to the negative n plus 1. Differentiating u with respect to x, we obtain u prime equals 1 minus n times y to the negative n times y prime, by this way. So u prime is equal to 1 minus n to the y minus n plus 1 minus 1 times y prime, following the chain rule of differentiation. And then we make the substitution into the equation 6.1.2 to get this equation. Now multiplying this equation by 1 minus n, we can get this equation: u prime plus 1 minus n times p of x times u equals 1 minus n times f of x. Now this equation is a first-order linear ordinary differential equation in the variable u. The solution of 6.1.1 is now given by this equation, y equals u to the n minus 1. So we need to solve this equation for u, and once we know u in terms of x, then we can know the solution of the equation 6.1.1, y as a function of x. Let's consider an example. Solve the following equation. xy prime plus y equals x squared y squared for x greater than 0. We begin by rewriting the equation in the form given in equation 6.1.1 by dividing the equation by x. So we get y prime plus y over x in the left hand side and x times y squared in the right hand side, as shown in equation 1. In equation 1, we identified that p of x equals 1 over x, f of x equals x, and n equals 2. Now dividing equation 1 by y squared to obtain the non-constant solutions, we obtain equation 2, namely y to the negative 2 times y prime plus y to the negative 1 over x equals x. Now we define the new variable u as y to the negative 1. Recall, u equals y to the negative n plus 1. In our case, n equals 2. And then we substitute the first derivative of u equals negative y to the negative 2 times y prime, as discussed earlier, into the equation 1 to obtain this equation. And then we multiply both sides of this equation by negative 1 to get this equation. Now we observe that this is a first order linear ordinary differential equation in the variable u, which has the following solution. U equals c times x minus x squared, where c is an arbitrary constant of integration, as you should verify the solution. Then the given equation in terms of y has the following solution. Y equals 1 over cx minus x squared, obtained from this relation, since y equals 1 over u. And then we substitute this expression here to obtain this solution.